Any questions about material thus far? Reactions of alkenes. Hopefully you see the consistency in the mechanism. Alkene reactions are something that you can put on your note cards. Like a line reaction on one side with no product, and then on the flip side show your product. You can also show on the flip side any particular details. So you're looking at a reaction and you can think, okay, what's that product and what other details do I need to know here? We were looking at synthesis of epoxides. Epoxide is similar to a bromonium ion. After that, oxygen back bonds, that's not intermediate, that's not really formed, not actually formed. First intermediate, and then we lose a proton, we can go neutral. Where here you cannot. These can be isolated. Epoxide. They tend to be reactive intermediates. Although there's a couple of drugs out there that do have epoxides. Like maybe even an anti-cancer drug. The epoxide is fairly reactive. Okay. Predict the product here. This is a predict the product question. Alkene, that's a peroxy acid, yeah. What is that? Dichloromethane, just a common solvent. Will never be a reactant. It's always a common solvent. You used it in lab last week, you'll use it in lab this week. You've got to get used to seeing solvents, so you know you can just ignore them. MCPBA, what do we got here? Boom, 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 boom. We're just going to connect an oxygen here and there, and there's your product. We can dress it up. Bone pairs. In terms of stereochemistry, that's not chiral, we just have a chiral carbon here. It's going to be racemic. And we will learn what that means over the next week or so. Basically, it means you can draw it two ways. You can draw that bond forward, and also you can draw it back. It's both.
So, when we're answering something like this on a quiz or test, is it okay to just put the asterisk there? Or do you want us to put the enantiomer with it?
That would be okay in places. You need to know what that means, though, in case you're asked to show it a different way or to clarify. Very common to do something like that. And we will clarify that going forward. Okay, down here we have a ring. Again, if we do not consider stereochemistry, I mean, many of these reactions are very straightforward. I mean, this week in lab, you're going to put a bromine on each carbon of the alkene. By the way, this is on the green handout. Is this A or B? I think there was two headings. We're under B, is that right? What is B? What type of reactions are B? No carbocation. Because none of these reactions under B have a carbocation, you don't get rearrangements. You only get rearrangements when you have carbocations. All right? These reactions, we're adding something across the pi bond. We're not going to get groups anywhere else. All right? Used to be alkene, now both carbons connected to oxygen. This week in lab, alkene, each carbon can be connected to bromine. But then also you might have stereochemistry. This week in lab, you have two potential stereoisomers. Actually, you have three. But those bromines, even though they're on the same, one is on one carbon, one is on the other, they can be projected differently. Okay, in terms of just what's the product, well, we connect an oxygen there and an oxygen there, right? And all that's connected, right? 6-membered ring, right? What about stereochemistry, though? Because typically we also need to know stereochemistry. The 2 bonds to oxygen, are they going to be cis or trans?
Cis.
Well, the answer is they're going to be cis. The methyl will thus be what by default here? Well, those are both forward. The methyl's going to be back. Plus an enantiomer. That over there is really what you need to be able to show as product. You need to also include stereochemistry in your product. Why are both bonds to the oxygen forward? Because if the peroxy acid is over here and the alkene attacks it, and the oxygen is now bonded here, if the oxygen back bonds, well, that bond's got to be forward as well. Because if the first bond is forward, the next bond has to be forward. So that's where the alkene attacked it towards the front, and both bonds ended up like this. So you could also have it where both of those bonds to the oxygen are back. And thus the methyl will be forward. Whenever we do enantiomers going forward, everything will be switched. All your dashes and bolts, okay? Again, with rings, stereochemistry is pretty straightforward if you figure it out there. The 2 at the bottom are a touch more difficult until I just kind of show you how to do it in the way I do it. Then up there. I think it's because, okay, I'm doing nomenclature. Is that alkene up there stereogenic? No. Everybody agree? No? All right. What about this alkene? Stereogenic? Cyclohexene, 1-methyl cyclohexene. Stereogenic? Stereogenic? Why is it stereogenic? No, it's not stereogenic. Pretty sure that was in the video, right? All right. This alkene, stereogenic? Okay, you need to know what stereogenic is, all right? Because I can't tell you the trick unless you know what stereogenic means, because if I tell you that and you don't understand that, then it's no worth, we can't continue on. Okay? Any questions about the nomenclature video of alkenes? Okay, the 2 below, basically, we'll do these. Well, I feel like we just should move on at this point. Give those a try. We can talk about a way I recommend doing that later. Next. Again, we're going along the green sheet, around the Wheel of Fortune there. Next should be cyclopropanes. Cyclopropanes, hydrocarbon. It's a cyclic hydrocarbon. Cyclo 3-membered ring, right? Yeah. These can be made from alkenes. There's actually a number of drugs that contain cyclopropane rings. Cholesterol drug here. Singulair. Anybody ever heard of Singulair? Cipro. cyclopropyl groups. Cyclopropanes can be made from alkenes. Of course, we're doing reactions of alkenes, and this is thus a sort of a common reaction. What you can do with alkenes, you can convert them to cyclopropanes. What's going on here? Basically, the two carbons of the alkene are still here. They're just going to bond to one additional carbon and make a three-membered ring. The epoxide was a three-membered ring. Yep. So they had oxygen. This is all carbon. One traditional way to do this is to react your alkene with diazomethane, CH2N2. It's called diazomethane. I could have asked you to draw a Lewis structure for this back in week 1. If you do that, you're going to find that you can't draw it without formal charges. And this is a typical Lewis structure for diazomethane. It's a toxic explosive gas. We will not be using it in lab. We can work with it on the board. All right. All right, if you heat this, it will explode. But if you heat it controlled manner, we can get chemistry. Okay, if you heat this up, this thing will break apart. This nitrogen's positive. This nitrogen would like to go back neutral. It can leave. It can take these electrons, become a lone pair, and now it's no longer bonded to this CH2 group. Well, now that is nitrogen gas. It's just N2. You're breathing it right now. But it leaves behind this guy. All right, this is condensed here, but it's a carbon. All right, let's draw this. It's a carbon with two H's. And the carbon has a lone pair. Does it have anything else? All right. Carbon with two H's and a lone pair, and a bond. And that's a negative charge, if you can do charge. The bond leaves. What do you have there now? That's it. There's no longer a bond here. What's the charge of the carbon now? There's no tricks. You can just do a formal charge. What's the charge of the carbon? Neutral. Yes. But is that a standard carbon? Standard carbon is 4 bonds, no lone pairs. Not standard. Now, early on, I said if it ain't standard, it's probably going to have a charge. I said probably, because there are cases where a non-standard atom can be neutral. This is an example. It's a non-standard carbon, yet it's neutral. Does this carbon have an octet? No, it's only got 6 electrons around. Yeah. This type of carbon is occasionally seen. It's called a carbene. A carbene. It's a divalent carbon. I mean, it's a carbon bonded with 2 bonds. Neutral, no octet. We could do every question here. What's the hybridization of this carbon? Can you graph the hybridization? It's sp2 with an empty p orbital. All right? No octet. Would that carbon like to have electrons? Yes, the carbon would like to have electrons. so it can fill its octet. The carbon's electrophilic. Okay? All right, this may be the first time. An alkene has attacked an H+, a C+, something like bromine that's schizophrenic and become partial plus. Proxy acid, we had the OO and we had partial plus. All right, these are all electrophiles. Because they're partial plus or plus, they like electrons. And the electrons are attracted to them. That's how you get reactivity here. This is acting as a nucleophile. Will an alkene react with this? I don't see any plus. Does it have any plus character? I don't know that it has any plus character. But it inherently wants electrons, though. It does not have an octet. All right? No octet. Thus, it's an electrophile. Electrophile is sometimes shown like this. Thus, an electrophile. Okay? Well, hold on. I drew that like that. What is these charges here? The net charge is neutral. It's neutral. A lot of times with carbines, some people show two charges. Because a carbon with a lone pair is often a minus. And a carbon missing an octet is often plus. This carbene has dual character. It acts as if it's plus because it doesn't have an octet. But it also has some minus character because of that lone pair. Okay? Or if you don't want to do this, just don't show the charges. It's just CH2 with a lone pair. I do it like this, and many people do, just to reinforce the fact that it has dual character. Down here. The pi bond attacks the carbon. It fills the empty p orbital. Calls that reagent's electrophilic. All right? And it's almost like it's attacking the positive character. But we're going to leave cation down here, left or right? On the left. So we make this bond to the carbon. The carbon now has 3 bonds in a lone pair. Well, now the carbon is minus. You can do charge, it's minus. But it's got a lone pair. What do you think it's going to do? It's going to immediately back bond. And when it does, what do you get? You're done. You get final product. From this point, how many intermediates in the mechanism? None. It's not an intermediate. It's not actually formed. This is just us on the board. This reaction is just boom, boom. Because these electrons are coming in here at the same exact time, right? You got that yet? Right? You're carbene with a lone pair. As I attack you, what is the lone pair doing? What is the lone pair doing? It's back bonding. So you back bond over here. There you go, cyclopropane. There's no intermediate. Okay? All right? That's it. This reacts with carbene to get your product. That's a carbon with 2 H's, right? There it is, carbon with 2 H's. It's analogous to the epoxide. At least with the epoxide, we had to remove an H to go neutral. Here, you don't even have to remove an H. You're done. Again, consistencies in the mechanism. What's new here? Dealing with carbenes. What's a carbene? How do we make it? Just a standard CH2 carbene is made from diazomethane, a little bit of heat. So this reaction generates this plus what? Plus nitrogen gas. Tipped it. The electrophile had to be generated. It's easily generated. A little bit of heat, this thing's going to fall apart. One molecule converting to 2, driven by entropy. Questions about use of diazomethane? Mechanisms consistent? There's another way to make carbenes. You can make them from chloroform. All right, 3 chlorines, not 2, not dichloromethane. Chloroform. And hydroxide. You can make a carbene here, but it's going to be the dichlorocarbene. If you use a dichlorocarbene, your cyclopropane is going to have 2 chlorines on the, what was the carbene carbon. Now maybe you don't want chlorines. Well, if you don't want chlorines, you're going to have to use explosive gas. This is typically shown because it's very traditional chemistry, and you can do this in the lab because chloroform is safe enough to use, hydroxide, common base. It's much more easy to do. And actually some students in organic actually do this reaction somewhere in the country. Here, how do we generate the dichlorocarbene? Chloroform. With hydroxide, it'll act as a base, take the H, these electrons stay here, right? Acid-base reaction gives this guy, it's an anion, plus water. What I hope you are confident in now and can do is readily see this acid-base chemistry and how we got to here and see the mechanism. You're good with that at this point? Okay? Yeah, you should have a lone pair here, right? It came from this arrow right here. Acid-base. This guy, of course, is an anion. We talked about how to determine thermal charge. Yeah, crucially important. It's an anion. At this point, this guy will fall apart. Carbon doesn't like being minus. By the way, we often don't talk about equilibrium. Can this go back? Sure it can. This can take an H from water and you can go back. You could do a pKa and say which side's favored. I bet you this side's favored. But a little bit that's formed can continue on. It can continue on by this chlorine leaving. You see, carbon doesn't like being minus. Chlorine, though, loves being minus. And they kind of say, okay, carbon, what if I just leave and take electrons with me? What does this arrow give? Cl minus. Leaving this as just 2 bonds to chlorine in a lone pair. Well, this carbon is now neutral, even though I showed 2 charges. Now neutral. So by the chlorine leaving, the carbon gets to go back to neutral. And chlorine is over here like, I like being minus, so we'll do this. And it's electronically it makes sense. Also, again, it's driven by entropy, 1 molecule becoming 2. And basically, you can generate this by treating chloroform with base. Now this is the carbene. And your alkene is now ready to react. Electrons come in. And of course, at the same exact time, this lone pair is back bonding, and there's your product. It's a dichlorocyclopropane. But this can be isolated, and this is a much friendlier reaction than using explosive toxic gas. But it also illustrates some nice fundamental mechanisms, fundamental chemistry. Predict the products here, okay? Alkene, what are we making here? I mean, diazomethane alkene, that's cyclopropane. There will never be anything else. What are we doing down here? What does this look like? Chloroform and hydroxide. Dichlorocarbene. It'll never be anything else. So these are, there's a little memorization, yeah. You just have to know that, hey, yeah, that's that reaction. Alkene with halogen and water, what are you making? Halohydrin, yeah. Okay. That gets you going. From there, though, then what's the mechanism? Then that's when more of your knowledge comes in. Can you use arrows, et cetera, et cetera. All right? Again, we can do this. This alkene here, we can draw it probably with an ugly bond angle. We're going to make cyclopropane here, yeah? Mechanism is up there. What's the stereochemistry here, though? What type of stereochemistry is even possible? Do it? No, that's only with carbocations. He said something like a ring expansion. No, that's a type of carbocation rearrangement. This reaction did not involve a carbocation. No, this is it. We didn't see a carbocation over there anywhere, did we? No carbocation shown on the page. I'll take that back. There's one shown on the page, but it ain't really formed. So no, there's no carbocation. What type of stereochemistry do you have? Do it? Cyclopropane is cis. Okay. Well, the type of stereochemistry I see here is you have a ring and two groups. Remember when we had a ring and two groups? We had something like this here. A ring and maybe two groups. These groups can be cis or trans, and maybe we drew one like this. Those two groups are what? Cis. Those two groups are, okay. You got a ring here. It's a three-membered ring. Got two groups on it. The groups can be cis or trans. That's the type of stereochemistry I would want you to see here. Are the two groups on your ring going to be cis or trans? I can't answer you because then you'll know what the answer is. Won't be cis. The two groups are not cis. Why do you say cis? Okay, that's the type of thing we need to understand. We looked at this, right? We looked at rings with groups. It's a very fundamental idea that we need to then be able to use that information. Just about anything I show you, we need to be able to use it. That's what you got here. You got a ring with two groups. All right? It's drawn kind of ugly, bond angle. Okay, here's how you need to do this. All right? This alkene is stereogenic. Yes. Okay. And I think, I don't know if that's enough to say that it needs to be done this way. I think so. This needs to be turned first. We need to turn this, we need to draw the alkene like this. Here, are these groups cis or trans here? Trans. we can draw these groups. This one coming like this. And this ethyl group going like this. These are the same thing. I've just turned it. Okay? Here it is on the board. It's supposed to be drawn exactly as it is on the board. What have I done? Look at these two groups. They're trans. If I turn my paper, keep an eye on this group here. When I move my paper, is it going to come towards you or go behind the wall? How's it now? There it is there. How's it now? Towards you, okay? All I've done here is I've turned it, instead of on the board flat, I've turned it like this. And that's supposed to be like this now. Now that group is coming towards you, and this one's going back. All right? There it is on the board there, flat. All I've done is do this. See, here the groups are up and down. But when I do this, now they're front and back. And now we can draw it like this. Most books are not going to do this. This is the way I recommend doing it. What we have to figure out is when. When do you need to do this, when not? Here it is. We'll clarify that. Now, let's do the reaction here. What do we know about this? We're getting rid of the pi bond, and we're connecting each carbon to what? A CH2. Or, yeah, this is a CH2. Okay? Like this. The carbene can come from the bottom or the top. Here it is. The pi bond comes down and attacks the carbon. It's got a lone pair. It's immediately going to back bond, and both of those bonds are going to be straight down. All right? So this no longer equals that. Now this gave that. And there's your product. And there's your ring. And the two groups on the ring are what? The trans. You see them? The trans. But guess what? You're also going to get the same exact setup used to be an alkene here. We got rid of it. We can also make the product like that. Because here's your alkene with two groups trans, but one's forward and one's back. The reagent can also attack from the top, or be up here. Pi bond attacks it, so that bond's up. Straight up, right? But then the carbene-carbon lone pair back bonds, and that bond is also straight up, but it came like this. Right? So you end up with this up. All right? We went up and attacked the carbon, it back bonded, and so both are up. Or both down. I would prefer you do it like this. I think it's cleaner and you're going to get the answer without less confusion. Books, however, are going to put these bonds front or back, like I think you were trying to do. I recommend new bonds in the plane. You see how the new stuff here is in the plane of the board? The original stuff front and back. Because the original stuff front and back is easy to do just by just turning that, and you don't have to even think. Just turn it. So you do have to think. All right? This is the way I recommend doing it. Here's your product. What's the relationship between these two? Your stereoisomers, what type? They're mirror images that are different. They're called enantiomers. In the future, we may say that plus an enantiomer. If we ever do that, well, that's the enantiomer. Remember how I told you when you do enantiomers, everything switches? Well, it looks like it hasn't happened. If you draw this ring up, like if you drew it exactly like that, these two groups would have been switched. More coming. At this point, this is in your notes, and we're seeing the first time of working one of these. Where I think if this is stereogenic, you need to do it this way. Okay, and one below is a ring, which is a little bit easier. We've done those before. Questions before we leave that page? Carbenes are sometimes seen other places. This is a drug, Paxil, I believe. So any drug in the body is going to be metabolized. Chemical transformation, and that metabolism has some mechanism, and it's a reaction. Now, a lot of times in the body, you use complex enzymes, but it's still, if you can boil it down, it's a fundamental mechanism. And the metabolism of Paxil, between these two oxygens, a carbene is formed. A divalent carbon with a lone pair, neutral, no octet. And I think what they're doing here is, I don't know, I haven't read it in a while. I think they're trying to prohibit this, and what they're doing is they're replacing these H's with deuteriums. Remember what a deuterium is? Right? Isotope of hydrogen. It was on one of the first handouts. Yeah? And a CD bond is stronger than a CH bond. Just a mass effect. And these CH bonds are broken when we make the carbene. And if those are deuterium, it's more difficult to do, and the metabolism doesn't take place as readily. You can do this as long as, if you make these deuteriums, it doesn't change the drug activity. Well, what's the difference between an H and a deuterium? Not much in terms of many things. Of course, the mass is twice as much, but it's not going to affect nothing on the molecular scale. Because what's the mass of an extra neutron? What's the mass of a neutron? It's something to 10 to the negative something, ain't it? I mean, another neutron ain't going to really make a difference unless you're counting beams. All right. So, carbenes. What's after? Oh, I see Gem. Gem dichloro. The dichlorocarbenes, the chlorines are on the same carbon. You can call that geminal dichloride. Gem dichloro. Gemini, what is Gemini? Twins? Okay. So a gem dihalo. We're in lab this week, we're making what type of dihalide? Are the bromines in lab this week on the same carbon? Oxymercuration, next topic. Alkene reacting with aqueous acid. Do this reaction, major product is this alcohol. How do we get that product? We're doing more than just working with these two carbons. Somehow we got the nucleophile over here. It looks like what happened? Like a carbocation rearrangement. Okay? All right? And indeed, that's the major product over there. But what if you wanted the oxygen to add here? Get this product. Well, you don't want to use just aqueous acid because you won't get this product. But we do have a way to get such an alcohol using this set of reagents. It's a two-step process, mercury acetate and water followed by sodium borohydride. This may be our first line reaction where we have two separate steps. Remember on the line reaction sheet where I told you about this, 1 and 2? You can even do 1, 2, 3. Okay. You do that. You can even perhaps isolate an intermediate. This is not there until you're done with that. Then you come in and react here. This can give sort of the alcohol that you would expect up here. Where are you going to make cation, right or left? Left. And the oxygen ends up where the cation would be without a rearrangement. That's sort of your outcome. Nucleophile on carbon where the cation would be is called the standard or Markovnikov product. We'll compare that to our next reaction. This reaction is called a oxymercuration or that, followed by reduction. That'll make more sense. Let's look at the mechanism first. Okay, what type of reactivity do we have here? Alkenes don't react with water, so we must be reacting here, yeah? Mercury acetate. Now mercury is a transition metal. You can maybe show it covalently or I'd probably show it covalent. You may have been told it's ionic. Transition metals can actually be either. You can show this like this. If we show it ionic, what's the charge of the mercury? 2 plus. What is OAC? What's the name of OAC?
Acetate.
Acetate, and what's its charge?
-1.
Minus, so you got 2 minus, and that'd be a 2 plus. Okay? Some books maybe show it like that. These can leave or ionize. If we have one leave here, this is going to give the mercury acetate, that's now positive, plus the acetate ion. Then we can have this one ionized, and you got 2 minuses, and you're left with the mercury 2 plus if you want to show it fully ionic. But the electrophile in this reaction is your mercury plus. Okay? These electrons attack the mercury plus just like it attacking an H plus. Where are we going to leave cation, right or left? Left, we've already answered. So we pulled away from that. I didn't draw the mercury up here, so I'm going to have to come over here and attack it. Coming down here, this is going to give boom, 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 boom. And then this is bonded to the mercury acetate. And cation would be here. Yeah? Mercury is now neutral. One thing we have to know here is that mercury has a lone pair. At least one. I'm not really sure how many it has when I think about it, but it has one, at least one lone pair. Because of that, what do you think is going to happen here? Is this really formed? No. These electrons are going to back bond, and what do we get? What does that give? Boom, 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 boom. Back bond. Still an acetate here. We can show it maybe with a bond to give us some room. It back bonded. So what do you think? You think this is actually formed, or what's the... No. As soon as the alkene attacks the mercury's back bonded. All right? Here we go. The charge of the mercury here. No, think about it. It's plus here. It gained an electron with a bond. It went neutral. From here, mercury owns both electrons. But here, it only owns one of those because it's now a bond. And so it owns one less. If that's neutral and it owns one less, this is now positive. That's a mercury. Remember we had the bridge halogen with a positive, a bromonium ion, chloronium ion. We had a bridge with a positive oxygen. Well, here we have a bridge with a positive mercury, called a mercuronium ion. It comes from the electrophile being attacked and back bonding. We get this. Do I have a bromonium drone over here? No, but I say it's similar to the halonium, right? Either bromine or whatnot, right? Right? Mercury's got an acetate. Okay, this thing cannot go neutral by losing an H. Instead, just like the bromonium ion, something comes in here and attacks. What attacks you? Water. These electrons. Where are you going to attack? Left or right? It's the same as over there. If we had a group here, where would we attack? Left or right? On the left. The answer is right here. Same place cation would have formed. All right? Except you don't attack a free cation. You attack okay, it's the same discussion as that over there. Water attacks here, and we kick this off. Let's finish this up. Well, we'll finish it up to just next structure because we're out of time here. What does that give? And you can finish it up on your own. Boom, boom. Mercury acetate opens up. Now bonded here is going to be water. We'll end one more here. Acetate. Acetate here. Acetate takes the H. And we get boom, 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 boom. Mercury acetate, and right here we have an OH, and we made acetic acid. Okay, and this is in step 1. We'll pick up here. All we need to do is remove the mercury. What do we need to do? How are we going to do it? How are we going to get to our final product? Have a good day, guys. See some of you tomorrow afternoon. I'm pretty sure we're meeting upstairs.